Hey, and today we're going to talk about chemical bonding. Now, this is a three-part presentation, so we'll go ahead and focus on the first section regarding chemical bonding. The three phases will feature discussions on covalent bonding, ionic bonding, and some empirical and molecular formula. But like I say, we're going to focus on just the ionic bonding aspect. And I hope that you're aware of the resource online via OpenStax, which features the chemistry second edition, and that's a wonderful tool, textbook to be used as a resource when you're studying and reviewing your information. Additionally, what I do in the video is I embed tutorials when needed, and in addition to that, if you find use, there are also guided notes that can be used to fill out as you proceed with the presentation. Now, the general overview of what I plan on covering today centers around ionic bonding. We'll talk about chemical formulas, some molecular and ionic compounds, and then end up with some things regarding nomenclature and naming ionic compounds. Now, the first thing you need to understand is what an ion is in general. And in its simplicity, an ion represents a charged atom. It is charged because in a neutral atom, you have a standard arrangement where you have equal numbers of protons and electrons. And when this number deviates or changes, it becomes an ion. Now, the only thing that can be lost or gained are electrons. And if you lose a proton, it would completely change the identity of the element you're talking about. So, once again, when the numbers of protons and electrons are equal, they're neutral elements, but when they become unequal, the atom becomes an electrically charged ion. So, a charge of an atom is equal to the number of protons minus the number of electrons. And so, since the number of electrons can change, that's going to impact the charge of that atom. Now, atoms and molecules acquire charge by either losing or gaining electrons, and we'll look specifically at the formation of losing and gaining a little bit later, but let's just talk about the types of ions that exist, because we mentioned that electrons can be lost or gained. Now, an atom that gains one or more electron can exhibit a negative charge, and that is called an anion. Now, anions usually form when a non-metal atom gains enough electrons to have a filled valence shell. For example, if you consider a neutral oxygen atom featuring the atomic number Z is equal to 8, that means it has 8 electrons, and if it gains 2 electrons, it will become an anion with a -2 charge. Mathematically, that can be expressed by thinking of it in the context of saying you have 8 protons, and you're subtracting that from the number 10, which would equate to the number of total electrons, and that would yield a value of -2. Now, as I highlighted, the ion that receives a negative charge is considered an anion, and so that would be a element species that features a -2 charge and therefore an anion. Now let's look at the other end of the spectrum. If you have an atom that loses one or more electron, it will exhibit a positive charge, and it is called a cation. Now, a cation is positively charged, and it becomes positively charged when the electron is lost. Now, think of it in this way. Protons carry a positive charge, and electrons carry a negative charge. So mathematically, when you take a neutral sodium atom that generally has 11 electrons and 11 protons, if it loses one electron, it will then therefore become electron deficient, meaning therefore it'll end up having 10 electrons. Mathematically, if you express this, you think of it in terms of 11 minus 10, it would yield a value of +1, which results in a positive charge. Therefore, it would be called a cation. Now, the cool thing about this is if you have a periodic table, and this is definitely useful to have or write on the side somewhere, you can actually predict the manner in which these elements will form ions. And if you look on the image that I've highlighted, on the left, you have elements that form what's called cations, and on the right, you have elements that are called anions. Now, these just highlight the tendencies of those particular elements. And notice that there's some similarities between these main group elements. What it is saying is that every element in column 1 will form a cation. Now, it will form a cation by losing 1 electron and becoming a +1 cation. Now, if you look in the second column, you notice there is a +2 designation located right above it. This indicates that the elements themselves become +2 cations. Recall that cations means that they are positively charged. They form these cations by losing electrons. Now, if we skip on down, you'll notice that there's a collection of them here, a small collection, if you will. But the one that you should take note of is this guy here where it says +3, where you have aluminum and gallium. Now, with those two, they will form cations as well. And they form cations by losing 3 electrons. Now, you notice there's a large amount of empty blue space. And part of that reasoning lies in the fact that this area located in the central region are referred to as transition metals. And transition metals can undergo several variations in their loss and gain of electrons. And so that has not been highlighted. What needs to be taken from this is that you want to know the specific main group elements that will form cations and anions. In this case, you have your cations in this group right here. And then you also want to recognize this group here, which forms your anions, which are negatively charged. This forms a -3 anion. This group forms a -2 anion. This group forms a -1 anion. And if you notice, this last column, forms a group that has 0, which indicates that it does not form an anion nor a cation. And that's primarily because these elements are stable. They prefer not to react further because they have achieved what's called octet. An octet indicates 8 electrons in this valence shell. It indicates stability for elements, and that is the holy grail, if you will, of what elements are seeking. Now, regarding the trends of these elements, because they all seek to basically achieve octet, they undergo these various changes where they lose or gain electrons and become charged ions. And that brings to term the vocab word isoelectronic. Now, if all of these elements, whether they're these first and second columns, which are losing electrons, or on the right, losing electrons, they're all seeking to achieve 8 on their outermost shell, and in many cases, they become what's called isoelectronic. Now, isoelectronic just means that an element has the same number of electrons, meaning it has the same type of electron configuration, but it features a different number of protons and perhaps even neutrons. It's a completely different element. So when you think of ions and ionic compounds, ions themselves actually form elements that are isoelectronic with other groups. So this means that, for instance, fluorine here, when it gains an electron, it would become isoelectronic with neon. Likewise with oxygen, if it gained 2 electrons, it would become isoelectronic with neon. Now, the cool thing that you can also take away from the slide is that you can predict the behavior of these elements based on their main group location. Any element in this first column is going to go through a process where they lose an electron. And that goes further here into the second column. They'll lose 2. Here they'll lose 3. Here they'll gain 3. They'll gain 2 here. They'll gain 1 there. And all with the goal to achieve octet. And in most cases, they will come together to form an ionic bond. Now, as I mentioned, the periodic table can serve as a guide for predicting ionic charge. Many of our main group elements lose enough electrons to leave them with the same number of electrons as an atom of the preceding noble gas. That means their goal to achieve octet can be mastered. Reiterating what I just stated, the group 1 column loses one electron and forms a cation that features a +1 charge. If you look at group 2, they lose 2 electrons to form a cation featuring a +2 charge. Now, many nonmetals gain enough electrons to give them the same number of electrons as an atom of the next noble gas. If you look at group 17, which is closer to the noble gas column on the right, they tend to gain 1 electron, form an anion with a -1 charge. And if you look at group 16, they gain 2 electrons to form an anion with a -2 charge. Now, examples of this are included. Examples such as calcium would be a classic example of a group 2 element that will lose 2 electrons to become stable. That means it helps them achieve octet. An example of bromine serves as the formating group that will form an anion, and it will actually gain 1 electron to become an anion. Now this happens through the losing or gaining of electrons. Notice the number of protons and electrons featured. In the calcium, you see there are 20 protons and 18 electrons in the ion representation. And when you look at bromine, notice it has 35 protons and 36 electrons, indicating a disparity between the number of electrons and protons. Now, here's the main takeaway from this. You need to understand that to form ions, they will either gain or lose electrons. The number of protons does not change, because if the number of protons changes, the identity of the element will change as well. Here's again me reiterating the idea of these guys forming these anions and cations. And once again, column 1 forms the +1, column 2 forms +2. If you look at column 3 over here, where we skip kind of the valley to the other side of our mountain, you have a +3 charge, which means they will lose 3 to become those charged element species or ions, if you will. And then if you move on further to this side of the periodic table with these 3, you'll notice that they will gain electrons to become charged species. And they can be represented by their charges, as we showed in the previous example with calcium and bromide. Now, moving from left to right on the periodic table, the positive charges of cations are equal to the group number. Moving from far right to the far left in the periodic table, the negative charge of anions are equal to the number of groups moved left from the noble gases. So that's kind of how we got those trends. Now this method, like I've reiterated, is a little bit less reliable for transition metals, and that's primarily because they can form different variations of charged elements. For example, copper can actually form a +1 or a +2 charge depending on the copper construct that you're working with and the reaction type. Also, iron can actually form either a +2 or a +3, and there are several other examples that form variated charges. And they're listed here in this image here. Now, the most reliable ones are the ones that we made mention of, and so those are the ones that you're going to want to document and make sure that you're fully aware of, because I can anticipate questions about them. But the ones that are centered around transition metals are a little bit more flexible, so don't worry about knowing all of the inner workings of those just yet. Just recognizing the trends of these guys and these guys, the left and the right, to form cations and anions respectively, helps with your familiarity of understanding ions. Now, ions that we've discussed so far are basically called monoatomic ions. That means they have one element and they form an ionic compound. However, there are examples out there called polyatomic ions, which are electrically charged molecules where you have kind of a group of elements and they have an overall charge. And then you have something called oxyanions, which are polyatomic ions that contain one or more oxygen atoms. Now, the main focus is going to be centered around the monatomic ions, but I wanted to at least equip you with the understanding that there are other types of ions so you can recognize the verbiage. Now, in ordinary chemical reactions, the nucleus of each atom, and thus the identity of the element, remains unchanged. This means that only the electrons participate in chemical reactions by either gaining, losing, or sharing them. Now, we've only talked about gaining and losing, and until we talk about covalent bonding, we won't talk about the sharing aspect of electrons. But the gaining and losing of our electrons will yield ions. Now, here's some examples of polyatomic ions. And for simplicity's sake, it just helps to recognize them and understand why they're called polyatomic ions. They're considered polyatomic ions simply because they have more than one element species participating, and they form an overall negative charge or a positive charge depending on what type of loss or gain of electrons. Now, if you notice, there are some examples where you have more than one charge. You might have a -2, you might have a -1, and it's possible to even have a -3 depending on the nature of the polyatomic compounds that you're talking about. But the main thing you want to take away from that is that the ionic bond is formed from the interaction of these ions and ionic compounds, and these ions are formed themselves by the loss and gain of electrons. Well, when this happens, the electrons get transferred, and in this transfer process, this is what forms the ionic bond. So it's a very strong interaction, and this interaction usually happens between a negatively and positively charged construct. So basically, if you picture something on the left side of the periodic table and something on the right, they interact to form ionic bonds. Now, ionic bonds are electrostatic forces of attraction. They're very strong attractive forces, and they result in these elements being pulled towards one another where an electron is transferred. Now, when you talk about a covalent bond, and again, we won't go into great detail in this part of the presentation, there's a difference in the fact that covalent bonds share the electrons themselves. They do not transfer them. There's not an electrostatic interaction. There's an actual sharing that occurs. And so compounds are either classified as ionic or molecular covalent on the basis of the bonds that are present in them. Now, here are some examples of some ionic compounds that you might want to be familiar with, as they're very common, and it gives you an idea of how these bonds form. Here you have NaCl, which represents sodium and chloride, and you have one sodium atom that gives up one electron, forming a sodium ion. So you have a sodium ion. Now you also have one chlorine atom that accepts that electron, forming what's called a chloride ion. And so while the sodium keeps its nomenclature the same, the chlorine becomes chloride ion. And so together, the ionic compound forms NaCl, which is sodium chloride. Now, if we look at the next example, you have calcium and chlorine. And one calcium atom gives up 2 electrons that forms a calcium 2+ ion, which we should have seen the example earlier of how it's willing to give up those 2 electrons to form the calcium 2+. Then you have 2 chlorine atoms, each except 1 electron, forming chlorine ions. The ionic compound calcium chloride then forms. Now, some properties that we can go over generally. Ionic compounds are solids at room temperature. They have high melting and boiling points. They're non-conductive in solid form, but they definitely become conductive in molten form. So that means they can conduct electricity when administered in some kind of aqueous media like water or melted. Now, sodium chloride itself has a high melting point of 801 degrees Celsius, and here's just kind of a classic example of how it's conductive. It can allow you to actually generate electricity. The image on the right is after it's become molten and heated. Now, ionic compounds form when metals readily lose electrons to form cations, and nonmetals readily gain electrons to form anions. And when a metal and a nonmetal react, the transfer of the electrons usually takes place. Now, the metal and nonmetals generally form these ionic compounds, so one rule of thumb in recognizing whether something's an ionic compound or covalent compound is maybe possibly looking at the location of the elements in question. Are they located on the left side of the periodic table and on the right-hand side, or you have a high likelihood of it being considered an ionic compound? And so they're held together by ionic bonds. Now, they are electrically neutral overall, but when they are placed in solution or aqueous media, they can become conductive. Now, the formula of an ionic compound must have a ratio of ions such that the positive and negative charges are equal. Now, this process is usually defined by charge balancing, and essentially what happens is you take the neighboring charges of each element and they crisscross amongst one another, forming new compounds. So if you look at the example, you see aluminum 3 plus and oxygen 2 minus, and they form aluminum oxide. And that happens when 2 aluminum plus 3 ions react with 3 oxide ions to give you 6 negative charges and 6 positive charges. Here's an example of aluminum oxide with trace amounts of iron, and interactions with those can be seen in many forms of birthstones. Now, many ionic compounds contain polyatomic ions, as does cations and the anions are both. So you got a little bit of a mix and diversity. You want to treat polyatomic ions as discrete units. Therefore, in many cases, you put parentheses just to house the entire compound, and the charge itself gets distributed amongst the entire element. For example, if you look at the example calcium 2 plus or calcium ion and what's called a phosphate ion, they form calcium phosphate, where you see the charge of +2 and the charge of -3 are kind of swapped between the two. Therefore, you yield 3 calcium 2 plus ions that gives you 6 positive charges, and then you end up with 2 phosphate ions, which give you 6 negative charges. Now, molecular compounds, which are covalent compounds, result only when these atoms share electrons, which is unique to that of ionic compounds, which happen as a result of actually the process of transfer. They exist as discrete neutral molecules, and are usually formed by a combination of nonmetals. Now, they often exist as gases, low boiling liquids, and low melting solids. Now, when it comes down to naming, the actual process of nomenclature has a few rules. Now, the compounds are identified both by their formula and their name. And so we'll learn about how to name the following types of inorganic compounds. And we'll look first at our ionic and molecular binary compounds. And we want to look at some ionic compounds containing polyatomic ions. So the first rule in naming them is you want to name your cation first, and you want to follow that up by the name of the anion. Now, a monoatomic cation is just given the name of the element. So in the case where we were talking about calcium ion, magnesium ion, sodium ion, those are the cations, and they're usually written on the left side of the chemical formula. And those are given just your standard names. Now, what you do on the right-hand side is if you have an anion, especially a monoatomic ion, you affix the suffix IDE. So that's where you got the name of chloride or fluoride or bromide. Those names get added or adjusted by using the IDE suffix. Now, a polyatomic ion is just given the name of the ion. And just like I've mentioned before, if you want additional information on the process of naming these ionic compounds, there is a wonderful resource that I would strongly encourage, which kind of goes over some examples and gives you a chance to see more of these cited names. And you're welcome to click in the link for the PowerPoint presentation. Now, here are some additional names just so that you can see it in action. You have sodium chloride, potassium bromide, calcium iodide, just to name a few. And what should be taken from this naming convention is, again, the cations, which are the elements on the left, keep their names intact. And if you look on the right, all of these elements on the right receive the IDE suffix at the end of the name to be adjusted. Here are some additional examples, but these feature polyatomic ions. And the only difference here is that you just name them with their polyatomic names. There are no adjustments made to the actual polyatomic ion name. So you have potassium acetate and ammonium chloride, which keeps the IDE. You have the sodium bicarbonate. You have calcium sulfate, which keeps the sulfate. So polyatomic ions keep their names whether they're anions or cations. Now, most of the transition metals can form two or more cations, which I mentioned, and the charge of the metal ion is specified by a Roman numeral written in parentheses. So they'll give you an example of that when you're talking about iron. Here you have iron 3 chloride. If it were iron 2, you'd have a Roman numeral 2. Here you have mercury 1 and mercury 2 oxides. And then lastly, you have copper 2 phosphate. And there are all other examples where you have copper 1 phosphate. And what happens is not only does the Roman numeral get adjusted to 1, but it would also reshape the structure in which the chemical formula is written. So this covers our branch of presentation on chemical bonding that centers on ionic bonding.